Dear students, in this video we are going to see a problem in linear time invariant system. The problem is a process x of t is given, which is the input to the linear system, with impulse response h of t given as 2 times e power minus 7t at the time t greater than or equal to 0. And autocorrelation function is r double x of tau is e power minus 4 mod tau. It is required to find path spectral density of the output process. As per the definition, when x of t is a WSS process, then the output y of t is also WSS. So we have the autocorrelation function r double x of tau. When we apply Fourier transform to this autocorrelation function, we get a spectral density. So we get like minus infinity to plus infinity e power minus 4 mod tau into e power minus I omega tau d tau. Just I am supplying this autocorrelation function into the definition. Since tau takes two different values, this modulus of tau, I can split into negative modulus negative tau for this negative limit and a positive tau for the positive limit. So these base is same, so we try to combine the exponential and we get 4 minus I omega into tau, and here it is e power minus tau into 4 plus I omega. On integrating this, we get exponential function integration is the same, right? So e power tau 4 minus I omega, and this coefficient of tau will come in denominator, and the limit varies from minus infinity to 0, and here it is like e power minus tau 4 plus I omega divided by minus of 4 plus I omega, and limit is from 0 to infinity. Just applying the limits, it is 1 by 4 minus I omega multiplied with upper limit e power 0. In the place of tau, we are putting the limit value, and lower limit is minus infinity, so that it will be e power minus infinity for the first term. Negative sign 1 by 4 plus I omega. Here upper limit is infinity, it leads to e power minus infinity, and the lower limit is 0, so we get e power 0. So simplifying this, it gives 1 by 4 minus I omega plus 1 by 4 plus I omega. On cross multiplying, we'll get this I omega minus I omega gets cancelled. 4 plus 4 leads to 8, and in denominator we have 4 plus I omega into 4 minus I omega, which leads to 16 plus omega square, as minus I square value. I square is minus 1, so negative of negative will take positive, so it leads to 8 by 16 omega square. This is spectral density of input. Now coming to the transfer function h of omega. Transfer function can be found by taking Fourier transform on unit impulse function, right? So Fourier transform of h of t will give you the transfer function. So we just supply the definition: minus infinity to plus infinity h of t e power minus I omega t into dt. Since our input impulse is involving time t, I use the integrator at dt. So here h of t is defined as 2 times e power minus 7t, and this is according to the definition. So since h of t is not given for any time t less than 0, we assume it to be 0, so that our limit will be from 0 to infinity. The negative part, it takes a 0, so the entire will be 0. Now combining the exponential, we'll have e power minus 7 plus I omega into tau into dt. So on integrating this, we get 2 times e power minus 7 plus I omega into t divided by coefficient of t, and the limit varies from upper limit to lower limit 0. Right, applying the upper limit, it is e power minus infinity, and lower limit is e power 0. So on simplifying, we'll get 2 divided by 7 plus I omega. This is transfer function. So anyway, to apply this transfer function in the result, we need magnitude square. So I just take modulus of z square, which is nothing but z and its conjugate. So here the transfer function is a 2 by 7 plus I omega. It is multiplied with the 2 by 7 minus I omega, conjugate of this first statement. So on simplifying this, we get 4 divided by 49 plus omega square. So we can use this result to get the past spectral density of output. So SYY of omega, which is equal to modulus of H of omega whole square into SXX of omega. That means your transfer function into spectral density of input will give you the spectral density of output. So that we get spectral density of output as 4 divided by 49 plus omega square into 8 divided by 16 plus omega square, which we have calculated these two earlier. Okay. So finally we get 32 divided by 49 plus omega square into 16 plus omega square, which is the spectral density of output. So for your practice, a problem is given. The same way you can proceed and get the solution for the output spectral density. Thank you.